Hello, everybody. Hello, hello. Welcome back to this week's lectures. I hope you had a great weekend. I hope you had plenty of time to go over the homework. Um, I also hope that you had a chance to look at how I worked out problem number 50 in your Saturday surprise. If you haven't seen that yet, go check out on Canvas. I posted a video on Saturday morning that basically shows you how to go through numbers 50 and 52 because I realized that both of those require the use of XL, which I haven't really covered yet in class. Okay, so I went ahead and gave you guys a tutorial for that. So if you haven't seen it yet, go ahead and check it out. Okay, we have finished chapter 14, so now it's time to move on to chapter 15, which is all about chemical equilibria. Okay, and I've mentioned this a few times, kind of in passing throughout this semester, and maybe a little bit last semester, but mostly this semester. But now we're going to get into the nuts and bolts of what a chemical equilibrium actually is and what it means. Okay. First up, we're going to talk about something called a dynamic equilibrium. We're going to define what exactly that means. Dynamic equilibrium, okay? And to do this, I'm going to step back into chapter 14 for just a little bit. In chapter 14, in the kinetics chapter, we talked about how rate goes up with increase in concentration of A, right? So if we have our simplified A goes to products, okay? And in general, we can also say that rate goes down with A decreasing, okay? Now this is a general statement. This is very general. And you'll notice that this is not true for zeroth order reactions. Okay? Not true for zeroth order. Zeroth order, if you remember, only depends on the rate constant. It has nothing to do with the concentration. Okay? So, but in general, this is a good way to describe what happens with a rate and with concentration. As the concentration of the reactant increases, the rate also increases, and as the concentration of the reactant decreases, the rate decreases. Okay, let's look at a specific example. Let's look at the reaction of hydrogen gas with iodine gas. Okay, and this is an example that we looked at previously in the last chapter, actually, to talk about its rate to make HI gas. Now these arrows here, this forward and backward arrow, indicates that the reaction can go forward or backwards. Okay, it can go forward and backwards. Now at the very beginning, before any HI has been made, this reaction can't go backwards because there's no HI to decompose. And as the reaction goes further and further, more and more H2 and I2 are consumed to produce more HI. Okay, so this forward rate is going to decrease over time because these reactants concentrations decrease, and HI's backwards reaction into H2 and I2 the rate is going to increase because its concentration is increasing. Okay, so to illustrate, oops, move this down a bit. To illustrate, let's have some box, okay, some airtight box, and we have H2 gas in there, have some I2, H2, I2, I2, okay. We have an equal mixture of H2 and I2. This is at time t equals 0, so nothing has reacted yet. Okay, we don't have any HI in the system. The initial rate is fast. Okay, so this is going to create HI, and we end up making some HI here. Let's make 2HI possibly. Okay, something like that. Okay, and once you reach this point, the forward rate slows down. Okay, it slows because there's not as much of the reactants for the forward rate left. Okay, all of those reactants except for one hydrogen and one iodine have disappeared. At the same time, the backwards rate increases. Okay, and this is because there's more HI in the system. So the concentration of HI has increased, so that rate has increased, and the concentration of H2 and I2 has decreased, so that forward reaction rate has decreased. Okay, so eventually, if you wait long enough in time, you reach a state where the forward rate, oops, well, let's draw our molecules in here first. So let's say we have 2HI, whatever, it doesn't really matter. Some amount of HI and some amount of H2 and I2 still in the system. Okay, so this is at T equals very long. Eventually you reach a point where the forward rate is equal to the backwards rate. Okay. The forward rate is equal to the backwards rate. That means that as fast as hydrogen and iodine can form together HI, as fast as that can happen, HI is decomposing backwards into hydrogen and iodine. Okay? So nothing is changing in respect to the concentrations. Okay, so the concentrations of H2, I2, and HI don't change. They don't change. Okay, because as fast as the forward reaction is going, it's equal to as fast as the backwards reaction is going. And this is said to be dynamic equilibrium. It's dynamic because the reaction is still occurring, the forwards and backwards reaction is still occurring. It's just occurring at the exact same rate, so nothing changes, and you have an equal amount of reactants and products basically forever. Okay, this is why it's called a dynamic equilibrium. So let's define that a little bit more formally. Okay, then got a little tongue tied there, sorry. The dynamic equilibrium happens when the rate of forward reaction is equal to the rate of backwards reaction. Okay, so the rate of the forward reaction is equal to the rate of the backwards reaction. Okay, so it's still balanced out, but it's dynamic. It has this dynamic part here because the reaction is still occurring. Okay, now let's look at this in graphical space. If something's hard to understand, draw a graph. It's my life pro tip for you. Okay, so on this axis, I'm going to have the reaction progress. And on this axis, I'm going to have the concentration of all the species. Okay, So in the very beginning, we start out with some concentration. Oops. Wow. Some concentration of HI and some concentration of some concentration of I2 and some concentration of H2. Okay, let's say that those two dots are there. And of course, at the very beginning, we have zero concentration of HI. Okay, there's nothing. There's been no HI that's made at time t equals 0. Okay, so as this reaction progresses, hydrogen and iodine decrease, something like this. Okay, and iodine also decreases, something like that. Okay, and at the same time, HI increases. Okay, something like that. Now, there comes a point in this graph where the concentrations are not changing anymore. And this is somewhere around here, let's say. Okay. So we have HI, we have H2, and we have I2. Okay. At some point, we reach a point in the reaction where concentrations don't change anymore. This is dynamic equilibrium. So everything beyond this line is at dynamic equilibrium. Okay? And that's kind of what is happening with the concentrations of these species, just to give you a little more full picture of what's actually occurring here. One thing I want to point out, and that's really obvious here and sometimes confuses people, is that concentrations are not equal. At dynamic equilibrium. Okay, so the concentrations of all of the species are not at all equal at dynamic equilibrium. That's not what dynamic equilibrium is saying. What dynamic equilibrium is saying is that they don't change with respect to time. Okay, so the concentrations remain constant in time. They are not equal, but they remain constant in time. Okay. So if we don't know that they're equal, how can we figure out their concentrations? I'll show you that. How do we know concentrations? How do we figure them out? We basically already have the tools to do this, and we learned them in the last chapter. Okay. Now recall an equilibrium. Oh, actually, you know what? Sorry, this might confuse you a little bit. We are going to introduce a new constant, and it looks very similar to constant that we did in the last one, the rate constant. Now the rate constant is a little k, so I'm going to draw it like that. That's the rate constant. Okay, this is a little k. Next we're going to, or right now we're going to introduce a new constant with uppercase k, okay, and this is the equilibrium constant. And it's an uppercase K. Big K. Big K sounds like an off-brand cereal brand. He wants a big K. I don't know why that's so funny. To me anyway, you guys are probably sitting there rolling your eyes. That's okay. That's okay. I can feel the eye roll through virtual space. Don't worry. Okay, so this might be a little confusing. I will try to write little k like a little k, but make no promises. All right, you're just gonna have to realize that when we're talking about equilibria, we are talking about big K or the equilibrium constant. Okay, So let's set up an equilibrium, a generalized equilibrium. Okay, so we have our two reactants happening here. A moles of A and B moles of B are reacting to form C moles of C and D moles of B. Okay, this is our generalized reaction. Now, we are going to make a definition. So at equilibrium, the equilibrium constant K is equal to the concentration of C raised to the C value times the concentration of D raised to the value of D stoichiometric number of moles of D within that reaction, divided by the reactants A raised to the little a times B raised to the little b. Okay? This is how K is defined. And it is always constant at equilibrium. Okay? So K is always constant. This ratio is always constant when you reach equilibrium in your reaction. Okay? So let's do a real example. Let's look at the reaction between N2O5. This is an equilibrium reaction. That's really bad equilibrium arrows. To create 4 NO2 gas and 1 oxygen gas. Okay, so this is a decomposition reaction. The rate, or the, excuse me, see, I'm already doing it. I'm already confusing them. The equilibrium constant, K, is equal to the products NO2 raised to the 4th power multiplied by oxygen raised to the 1st power, because this number here is a 1, divided by N2O5 raised to the 2nd power, because 2, 4, 1, those are the stoichiometric values in the reaction itself, and that's what we're raising the concentrations to in this expression. Okay, so that's how you formulate the equilibrium constant. As long as you figure out the concentrations, and if you know the concentrations, you can figure out the equilibrium constants. Okay, so let's look at another example. Let's decompose some methanol to form, and this is a gaseous reaction, to form carbon monoxide and hydrogen. Okay. What is the equilibrium constant? Well, we can form it right away in terms of the concentrations. This would just be products. There's a 1 there because of the stoichiometric 1. Products multiplied together divided by reactants. Okay. Oh, that's a really bad C. Might not be so clear. There we go. Okay. This is the equilibrium constant. You might be asking yourself, okay, interesting, I follow, I can figure out how to do this, but how in the world does this help me figure out concentrations, and why is it so useful? Okay. Why is this so important? Well, we can make some generalizations. Okay. We can say that when K is much greater than 1, the forward reaction is favored. Oops. Okay. That means that basically the forward reaction is going to be much more significant than the backwards reaction. Okay, and if you recall what the equilibrium constant looks like, it's products over reactants, right? Products raised to the n over reactants raised to the n. In this case, the products are winning out. Okay? The products are winning out, so K is much greater than 1. So that means that the forward reaction is favored. Okay, so that's first case. Second case, how about the opposite, when K is much less than 1? What can we say? Well, in this case, we can say that the reverse reaction is favored. Basically using the same logic as above, the equilibrium constant is equal to the products over the reactants. Okay, and in this case, it's much less than 1, which means that the denominator is dominant. Okay, so that means that the reverse reaction is favored. There are more reactants present, the concentration is higher, and therefore K is much less than 1. Okay, let's look at some actual numbers here. So if we look at the reaction between hydrogen and bromine gas to form hydrobromic acid, okay, if we look up the equilibrium constant for this, K is equal to 1.9 times 10 to the 19 at 25 degrees C. Okay. This is a huge K, huge. Okay, so K is much, much, much less than 1, or greater than 1. So that means that the forward reaction is favored. Okay, so this favors forward just because that K is so huge. And if we look at a different reaction, say the reaction of nitrogen with oxygen gas to form NO gas, in this case the equilibrium constant is equal to 4.1 times 10 to the minus 31 at 25 degrees C. Okay, so this favors the reactants. K in this case is much less than 1, so this favors the reactants. Okay, and we're actually kind of lucky that that this reaction favors the reactants here, because our atmosphere is mostly composed of nitrogen and oxygen, and if the forward reaction were favored here, our atmosphere would instead be full of NO gas rather than N2 and O2 gas, which we use to respirate. Well, we don't use nitrogen. It's more like an inert carrier gas, but the fact that it would eat up all the oxygen would be a big problem for us. Big problem. Okay, so it's the little things in life that you should be grateful for, and every time I see this, I'm like, man, I am so grateful that that equilibrium constant is so tiny. Otherwise, I wouldn't be breathing anything. I wouldn't even exist. Okay, so that's when K is much greater than or much less than. What about when K is approximately equal to 1? When K approximately equals to 1, neither the forward or the backwards are favored. Okay, neither the forward or backwards. And in this case, the reaction proceeds to about the halfway point. Okay, so about half of the reactants are consumed to produce about half of the products that can be formed. Okay, so I'm gonna pause there for part 1. If you guys need to get up and stretch and get your snacks or whatever you need to do. Go ahead and do that, and I will see you for the next part in part two coming up.